Okay, I'm going to try to go through these. I don't know how well this will go, but basically, if we look at this first question, what is the kinetic energy at the top if the ball starts from rest? Well, the total energy, if it's at rest at this point, the total, right, is just what it had for potential. So I'm thinking it's going to be mgh. I shouldn't say that. Maybe I take that back. If it starts from rest, really the kinetic energy is zero if the velocity is zero, right? Now, what is the velocity at the bottom if the ball starts from rest? Well, at the top it had mgh as its total, right? And that should equal 1/2 mv squared. So if we try to solve for v, we're going to take this out. We're going to get a 2. So the velocity for this is going to be the square root of that, right? Because if everything at the bottom here, all potential has turned to kinetic. Right, what is the change in the potential energy? Well, the potential energy at the top was mgh. The potential energy at the bottom was 0. So the potential energy should be basically minus mgh, I would think. I'm not sure what z means necessarily. Z final, if that's the height. That's the height final minus height initial. So that probably would be that answer. And then really you just need to understand how to set up the problem. So let's look at the next sign. I was just going online to get some equations, right? But conservation of momentum really is m1 delta v v2 equals negative m2 delta v. This is probably a 1, right? Delta v2. So the momentum is conserved. We'll talk about that in a minute. The equation for finding the center of mass, m1 x1 plus m2 x2 over m1 plus m2. I actually found a thing in here. Let's see if I can find it. This is really what we were talking about. You'd have some reference point that you measured from, okay, to find that center of mass. So let's go back here. Let's go here. Let's do this example. The important thing is right now this cannon is at rest, right? But we are going to have the cannon shoot a ball at the speed, shoot a cannonball at the speed, so the ball will have a speed of 150 meters per second. And the ball has a mass of 15 kilograms, and the cannon itself has a mass, right, of 450. So m1v1 had better equal m2v2. So let's see, the ball of 150 and its 15 kilograms and its mass is 15 had better equal mass 2 times the recoil, which is what she's going to look at on the next thing here. Now they're different directions, but the momentum will be conserved. One direction will equal the other. Okay? So we'll know a velocity that'll get this thing up the hill. Alright. So first we consider the firing of the cannonball. And second we consider the recoil of the cannon. So there we're going to talk about conservation of momentum. Once we have that, we can figure out the next step. So let's look. Alright, so conservation of momentum is the first, conservation of energy is the second. So I said momentum was m1v1 equals m2v2, right? And really, v2 in this case is the initial velocity of the cannon, isn't it? So we're going to use conservation of momentum to start and conservation of energy second. So what we end up with are two equations. This one had to do with the recoil, and then secondly, taking the initial cannon to the final cannon, right? So we have the mass of the cannon. Its velocity initial is the same as the velocity recoil. Its initial height is 0. You're trying to find how far up this hill it's going to go. The final velocity will be 0 when it stops. We're trying to find this. We know everything else in this equation. So if we do it 1/2 mass of the cannon, 450, V initial. Now V initial is the same as V recoil. So if we solve V recoil, that actually equals mass of the ball, 15, velocity of the ball, 150, over mass of the cannon, 450. So I'm going to plug that in right here. 15, 150, 450. And goes away. Now, this second term for the cannon will be 0 because he's sitting at z equals 0. Equals 1/2 mass of the cannon velocity final, that will be 0, plus mass of the cannon height final. This height final is the only thing we don't know, and we can solve for that. Alright, moving on. We do have enough to solve this. Now this is one I was a little wondering about. So, energy is conserved for 1. So his energy up here is mg24, isn't it? We don't even care what his mass. Oh yeah, we do. 3,300. So we can figure this out. 3,300, 9.8, 24. Now, when he gets down here to what we're going to call 0, all his energy is kinetic, isn't it? So we can figure out his velocity right here. So we would say the 3,300, 9.8 times 24 had better equal 1/2 3,300 velocity squared. So we could calculate that velocity. Now down here, momentum is conserved as these guys come together. So the mass 1 times the velocity 1, which we just, plus the mass 2, velocity 2. Now this guy's sitting at rest, so he doesn't have any momentum. Will equal the velocity of the car, the combined, I'll say, m1 plus m2, right? And they're saying if we figured that out, that it could only climb at most 6 meters. So I'm really not sure about that, but I think if you do the calculations, this velocity and this mass, if at the bottom of the hill you look at it as 1/2 m1 plus m2 v combined squared equals mgh, m1 plus m2, 9.8 h. They're saying that should be only 6 meters. So give those a calculation and see if that works. Alright, these are kind of interesting. Describe the motion of a particle which has an initial position at x equals 3. So his initial mgh, right, was mass, looking for the mass of the, okay, mgh, if his total initial, initial total is 2.5, right? Okay, so his total is 2.5, the upper limit. This bottom of the ball can't go higher than this for conservation of energy. Alright, so let's see what, oops. I thought there was something in this slide that we needed. So 2.5. Now, if he's sitting up here, you know, right now, his velocity is 0, isn't it? Okay, so his mgh is 2.5. You could actually figure out the mass, couldn't you? Because we know what gravity is. Well, we really don't know height, so I guess we don't know much. We could figure out m and h. But if his total is 2.5 as potential, it's never going to go higher than that, right? Because if it went higher than that, it would have more energy, and we know that the energy is conserved, right? It says, at which points would this particle move toward the left if released from rest? Well, any of these positions we really don't know, but we can tell that it's going to move right here, and it's going to move left here. It's kind of an interesting they're removed from rest, because if you look here, he's got rest would be 0. His total potential energy on this chart is 3, so it's got to move down because it's going to give away some potential to give it some velocity. Same here. Right. Now it says if a particle at point D has a kinetic energy of 1.5, it's going to have 1.5 kinetic. Plus it's got some velocity, doesn't it? We don't know what it is. Let's see. How would they know what it was? Oh, it has a kinetic of 1.5. It does. And then it has a, let's say, a potential of 1.2. That's what it's getting. It's trapped between about 2 meters and about 5.5. Because your total has to be 2.7, right? Therefore, it's going to max out at a potential of 2.7. So they said 2.7. They came over and they went to those points, right? If it's as high as it's going to get, they're just looking at the total and they're saying at these points, at its max height, it's got to be totally 2.7. Okay, now that's all I got on this. I'm sorry I don't have a little bit more. Let me know if you have any questions, okay?